Okay, hi guys. It's Ms. Vermeer again. So we are still doing electrodynamics. And my PowerPoint isn't working. Just give me 5 seconds. Ugh. Sorry, technical difficulties. Okay, so I just quickly wanted to go back and just re-explain the topic that I did yesterday and make sure that we're all on the same page and we can all identify which way the current will go in a system. Yes, yes. Is it working now? Okay, sorry. Okay. Looks like it's working. So I'm just going to go back to the whiteboard. Just redraw that magnetic field and the coil system that I drew yesterday. And just re-explain how we determine which way the current is going and how we differentiate between an alternator and a battery, for instance. Okay, so if I had this coil in here and I've got my pink coil and I've got my green coil, and we now know from grade 11 that if you take a coil and you put it inside of a magnetic field and you move that coil up and down, you will be able to induce a current. So you'll be able to make the electrons in your coil flow from one side to the other. And then we learned about Faraday's law, about where your coil has to be in terms of the angle with the magnetic field and what type of current you're going to get, whether it's maximum current or no current at all. And then we learned Fleming's law, which is the right-hand rule. So we're just going to determine which way the current flows in these coils again. So I'm going to draw first. So let's say we are going clockwise again. First, we're going to figure out which way the current is going in the pink wire. So your thumb is going to point in the direction of movement of the coil. In this case, it's going to go point upwards. So you take your right hand and you point it upwards, because that is how my coil is moving. Then my index finger is going to point in the direction of my magnetic field. And no one realized that I drew it the wrong way around, which always goes from north to south. So my index finger is going to go to the left. So that is my magnetic field. And then it means if you're holding your hand now, your thumb is pointing upwards, your index finger is pointing to the left, then it means that your middle finger is coming out of the page or out of the screen, in my case, and that is my current, the direction of my current. So the pink wire is going to go this way, the current. Then if I do the same thing for my green wire is still, the thing is still going clockwise. So my thumb will point downwards. My magnetic field is going from north to south. And if you take your hand and you hold it, you will see that your middle finger is now pointing inwards. And that means that my current has to go up. So it means that my current has to go from left to from right to left in the system. Okay, and then remember over here, because of Faraday's law, when my coil is lying like this in my magnetic field, where it's lying parallel, you've got a cosine of 0 degrees, and that means that you'll have 1. So this will be my maximum current. If, on the other hand, I have this system where my coil moves and it is perpendicular, oops, like over here, and we use Faraday's law, we know that cosine of 90 degrees is equal to 0. So in this case, there will be no current, and this is where your current changes direction. Direction. Okay, so do we all still remember this from yesterday? We can all determine this. If I had to ask you a question to determine the direction of the current, you would all be fine with it. Can I get more thumbs up? Okay, and then just to double check, the way we could determine whether it was AC current or DC current, if they gave us an image, would be that if it was AC, your system would look like this. And you would have your slip rings touching your carbon brushes. Newton, what am I re-explaining? Which part? Just tell me which part. So remember that for your AC current, the one that's changing, you've got your slip rings. And that just allowed your coil to continuously turn without the wires getting crossed, and they keep touching this carbon brush. And so when you get to this position over here where your direction changes, and we go to where it's turned the other way, you will get a different direction. Okay, so Newton, what you do is you use your right hand and you're going to point your fingers, okay? Your thumb, yes, Luke, the slip rings are the purple and green circles. So the purple circle just means it is connected to the purple wire, and the green circle means it's connected to the green wire. So as your green wire and your purple wire is turning clockwise, it's changing direction every half cycle. And because it's got the slip ring, it's continuously touching your carbon brushes. So it is changing direction, the current. I'm going to show the split rings just now. I just quickly want to help Newton. Okay, so we're going to look at the purple wire first, Newton. You're going to take your thumb, and your thumb has to point in the direction that the wire is moving. So in this case, my purple wire, because this whole system is moving clockwise, is going to go down. So you take your right hand and you point your thumb downwards. Okay, so this is my thumb and it points downwards. Then your index finger always points in the direction of your magnetic field, and it always goes from north to south. So if you're holding your thumb out, down on your right hand, then your right index finger is now pointing to the left. Okay, so this is my index finger, which is my magnetic field, which we indicate with a V. And then if you now take your hand, you will see that your middle finger is naturally pointing into the screen. So it's pointing backwards. Where your middle finger points is your current. So in this case, this wire now has a current that goes that way. If we do the green one, we're going to take our thumb and we're going to point it in the direction of the coil. Coil is moving clockwise, so my thumb is going to point upwards because that is the way the green wire is going. My index finger is going to point to the left because that is the way the magnetic field is going from north to south. And now my middle finger is pointing towards me, away from my screen, outwards. So my current is coming out this way. Does that make sense, Newton? Do you understand how to do it? You use your right hand, your thumb points in the direction of the coil's movement, your index finger points in the direction of the magnetic field movement, and your middle finger is then telling you where the current is going. And what we said for AC current is, if you now look at this picture number 3, and you compare it to number 1 over here, the purple wire's direction of current has changed, and the green wire's direction of current has changed. And what we saw was that if we use split rings, then we can allow for this change in direction to occur. But if we wanted it in one direction, so if we wanted DC current, then we would use split rings. And they just look like these half moon shaped, half moon shaped circles. And then for your other side, and there is this gap here in the middle where they are not touching each other. Okay. And so as your wires would technically change, the current would change direction in your wires, your overall current would stay in one direction because of the fact that these split rings would always just touch the same carbon, the different carbon brush when it is in the same position. So over here, this carbon brush, okay, would always get the current going into it, and this carbon brush would always get the current going out of it, and it's not going to change because of the fact that you have these split rings. So Luke, what we're basically saying is, if you look at picture number 1 over here, and you look at your colored wires, in the first picture, and this purple one, your current is coming out of the page for the purple one, but over here in picture number 3, it's going into the page. So do you see in that colored wire, the direction has changed? So Mason, split rings is for AC current. Okay, so it means that it's always going to touch the same carbon brush, and split rings is for DC current, and it means that the same direction current is always going to touch the same carbon brush. So here, this purple one keeps touching this carbon brush. So no matter what direction and flow of current it has, so whether it's picture number 1 or picture number 2, it's touching that carbon brush. So the current in your system is going to continuously change. But if you've got this DC system where you've got the split rings, the different carbon brush gets touched by the split ring. So it's only going to get touched when it's going one direction. So let's say it's going this direction. As soon as the purple's wire's direction changes, the other half is going to touch this carbon brush again. So it's only one direction. Sure. Let me quickly draw it. Okay, so I'm actually just going to draw it onto this picture here, onto picture number 1. No, Sean, split ring makes a DC. So look at this. Okay, so if you're in position number 1, it means my current's going to go this way through my light bulb, right? Okay, when it then gets to position number 3, this happens. So what is happening is every single time the current in one of your wires is going this way in your system, that wire's half moon split ring will touch this carbon brush. And that's going to mean that the current's going to go one direction. Over here, your purple wire is coming this way. So its split ring is touching this carbon brush again. So every single time your wire changes, the opposite wire will touch the split ring. Does that make sense? So slip ring, slip, it's round, it can slip onto something, is AC. Split ring, where there's split, where there's a gap, is DC. Does that make sense? Do you guys see the difference now? Okay, cool. So that was just recapping from yesterday. And now we are just going to continue with the example question that we had, and then we can look at some past paper questions. So let me just change my screen. So we did RMS yesterday, so your root mean square for your current and your potential difference. Yes, Maison, but it also tells you that you have to look at whether you've got a slip ring or a split ring to tell you whether you would get AC current or DC current. If they give you a split ring, it's going to be DC automatically, and if they give you a slip ring, it's going to be AC. Okay, so we learned how to work out the root mean square current and voltage for your AC systems, because you don't have to do it for your DC because of the fact that DC systems have a constant current and voltage. Now we're just going to build on that, and we can actually work out power. So we can actually work out the average power of a system using the root mean square current and potential difference if you multiply them together. Or we could break up the formula and go write it, because remember, IRMS is equal to I max over square root of 2, and VRMS is equal to V max over square root of 2. So if we substitute those equations in, then you can get them equal to this. Square root of 2 times square root of 2 just gives you a half. So your formula could also be power is equal to half I max times V max. And so what they could ask you is they could say, the transformer for a laptop has the following information. You've got your input potential difference from 100 to 240. You've got your current as 1.5 amps and your frequency as 50 or 60 hertz. Then your output value is 20 volts and 3.25 amperes for your current. And then they say, using the input values and assuming 240 volts, what is the average power dissipated in the transformer? So what we go and do is we have to find our, so I'm going to do it both ways because there are two ways that you could do it. You could just go and use that formula where it's a half times your Vmax and Imax. And they told us that we're working with the 240 volts. There was only one current, which was 1.5 amps. And so we can literally just multiply it. And if you put that into your calculator, you should get 180 watts. Or, so that was the one way of doing it. Or we could go and work out the VRMS first, which is your Vmax divided by the square root of 2. So 240 divided by square root 2. And that would give you 169.71 volts. And then we work out our IRMS value, which is your I maximum divided by square root 2, which is 1.5 divided by square root 2. And if you put that into your calculator, you should get 1.06 amps. And then you could plot that into the formula where you're just multiplying the two together. If you plot that into your calculator, you will get a value of 179.89 watts. So what you'll see is, even though your answers are quite close to each other, they are slightly different due to decimal points. And on the marking memo, they will have taken that into account. So they'll obviously have all the methods that you could possibly have worked it out. So you wouldn't be more correct using the one formula than the other. So it's your choice. Just make sure that you substitute the right values in. Okay, so that was the theory bit. Let me just go to the past paper and we can start looking at past papers. Okay, so this is the 2018 paper 1, question 10. And they give you this picture for 10.1 and they say, in the simplified AC generator below, the coil is rotated clockwise. And 10.1.1, they ask you, in which direction does the induced current flow in the coil? So you guys can think about it so long, and I will put it into my whiteboard. And I see you guys already have the answer. Well done. Okay, so sorry, I do not know why my computer is being so difficult right now. Okay, so just going to draw my little hand. That's not a hand, that looks like a hand. So what you have to do is we have to remember that we are going to look at the direction of the coil. So in this case, the arrow is pointing clockwise, which means this coil is going to go upwards. So I take my thumb and I point it upwards. Then my index finger is going to point in the direction of the magnetic field, which is from north to south. So it's going to point left. And that means that my middle finger is going to come out towards us. So our current is coming out. So if you then draw it in, if you then look, it means that it goes from Y to X. And you guys had it right. Well done. See, this is easy. Okay, so we can just write that. Y to X. Then the next question says, on which principle or law is the working of generators based? So which principle or law do you guys think it is? Who that you learned about last year? It is Faraday's law. Yep. Thanks, Carl. Lisa Kanya, you are on fire today, I see. Then they say, state the energy conservation that takes place while the generator is in operation. So they're basically asking you what type of energy conversion is taking place. So you have to say that we are going from mechanical energy to electrical energy. Ooh. Energy. Okay, so that's all they're asking. When they ask you to state the energy conversion, they're just asking you what energy are we moving from. Then question 10.2, they tell us the voltage output for an AC generator is shown below. And they ask us to write down the maximum peak output voltage of the generator. So what do we think the maximum peak output voltage of the generator is? Yep, you just look at where your curve is turning, and that is at 340 volts. If you were to say negative 340 volts, they would mark it correct, but always just try and use the positive values for these questions. The negative is just indicating that the direction is changing. Then they tell us a stove is connected to the generator above and delivers an average power of 1,600 watts. 10.2.2, calculate the RMS voltage delivered to the stove. Okay, so just gonna get my whiteboard. They wanted RMS value. So V RMS is equal to V max over square root of 2. So in this case, we said that our Vmax was equal to 340. Cal, no, I've never seen one like that. I don't think it's impossible. It's just indicating which direction you're going in. It shouldn't matter though. But no, they'll generally give it to you as a positive graph. So 340 divided by the square root of 2, if you plot that into your calculator, I get 240.416. Yeah. If you round that off. Yes, thank you. Okay, then the next question, let's just go see what they asked. Question 10.2.3, they ask us to calculate the resistance of the stove. Okay, so I'm going to show you two ways in which we can do this. On your formula sheet, you will get a bunch of formulas. And one of the formulas will show you that P is equal to V RMS squared over R. So this is the one way that we can do it. So I'm just going to rearrange my formula before I plot in any values because I like doing that. But if you plot in values directly, it doesn't matter. So we know from the paragraph that our power was 1,600. And we just worked out our VRMS to be 240.42 squared. If you plot that into your calculator, I get 36.126, blah, blah, blah. Always round off to 2 decimal places. So 36.13 ohms. So that's the one way that you can do it, using that formula. The other way would have been using this formula. So your average power is equal to your root mean square current times your root mean square potential difference. So then set that in there. And you work out your IRMS. And then I would take that and just put it into my normal formula. R is equal to V over I. In this case, you use your RMS values. So it would be and you get similar answers, but like I was showing in the previous questions, your decimals will always be slightly out. So there are two ways. There would be more ways that you could work it out because your formula sheet has about 3 or 4 formulas for average power on it. You can pick and choose whichever one you want to use, basically. Okay. So does that make sense to everyone? Okay. So then the next question is a 2017 November paper, also question 10. And so 10.1, they tell you the diagram below shows different positions, A, B, C, D, A, of the coil in a DC generator for a complete revolution. The coil is rotated clockwise at a constant speed in a uniform magnetic field. The direction of the magnetic field is shown in the diagram below. So then they give you the images and they ask you 10.1.1, write down the energy conversion that takes place during the operation of the DC generator. Yep, so we are going from mechanical energy to electrical energy. Oops. Okay, then they ask us to sketch a graph to show how the induced EMF of the generator varies with time and clearly indicate the position A, B, C, and D, and A on the graph. So I'm just going to copy this image quickly and go to my whiteboard. Okay. So DC current, so I know my graph's just going to stay on one side of the x-axis. So this is time in seconds. And then this is induced EMF, which is voltage. Yes, Cal, I like your graph. So it'll look like this. Okay, obviously my curves are going to be exactly the same size. I just can't draw like that using my mouse. And then we have to put in where our points A, B, C, and D is. So important thing to note here, your A, C, and A are both when your coil is perpendicular to your magnetic field. So that means it's going to be these spots. So this is going to be A, C, and oops, and A, because that's the point where you have no current. Okay, they're perpendicular to your magnetic field. Cosine of 90 is 0. You won't have a current flowing through your coil at that moment in time. Then your B and your D is the point when it's parallel to your magnetic field. So this is the point right here where you've got your maximum velocity, voltage. So if this was your V max, like I say, my things would be exactly the same size. So your V max. Okay, so does that make sense? You just need to remember that your DC current, both of your bumps or curves are on the one side of the x-axis, and you need to be able to identify when your coil is perpendicular to your magnetic field, and when it's perpendicular to your magnetic field, there will be no voltage because there's no current going through it. So that is when it's on your x-axis. Okay, then let's see what the next question asks. So then you've got a question 10.2, and they tell you a small AC generator providing an RMS voltage of 25 volts is connected across a device with a resistance of 20 ohms. The wire connecting the generator to the device has a total resistance of 0.5 ohms. Refer to the diagram below. 10.2.1, write down the total resistance of the circuit. Okay, so total resistance of the circuit. Let me just put this into a whiteboard. Oops, why is this the wrong one? Sorry. There we go. That's the right one. So I just want to mention something because I did not mention this yesterday because we hadn't been looking at electric circuits yet. But when they want to show you something as AC currents in an electric circuit, they'll give you this weird circle thing and they make like a squiggly in it. And that is indicative that you are working with AC current. If they give you the normal battery system where you're going from positive to negative, that would be DC. So if they give you, and you will see the example that we do tomorrow, if they give you a circuit looking like this, for instance, and they've got this squiggly line inside of your circle, it means that it's AC current. That's just a side note. Okay, so they were asking us to get the total resistance of this circuit. So total resistance means that your internal resistance plus your load resistance load. So R load, which is your device, plus your R, or we can actually just use a little r, because everybody knows that your internal resistance is equal to R total. So it would be your 20 ohms from your device, as well as your 0.5 ohms that comes from the wires. So your total resistance would be 20.5 ohms. Does that make sense? Total resistance is always everything added together. Okay, then question 10.2.2, calculate the average power delivered to the device. Fun one. So now we want average power, and I'm going to work it out. First I'm going to calculate my IRMS. So my IRMS is equal to my VRMS over my total resistance. And they told you that you've got an RMS voltage of 25 volts. So it's 25 divided by 20.5, which we just worked out. And that gives it to 1.2195. If I round that off, I get 1.22 amps. Then secondly, I'm going to work out my average power that is being used in my internal resistance or from my wires. So that is equal to your current squared, RMS current squared, times, I'm going to use this 0.5. So I'm going to say little r. So it's just 1.22 times 0.5, my current's being squared. And that gives me a value of 0.7442. I know we're running out of time. Let me just finish this and okay, so that is for that one. And then I'm going to work out my power for my whole system. So it's just going to be my VRMS squared over my R total, which is equal to the 25 squared divided by my total R, which was 20.5. That gives me a value of 30.4, rounded up to 9 watts. And now I'm just going to subtract this value by this value to get my actual power. So my actual power is the power that was used by my whole system minus the power that was used for the internal resistance. Okay, does that make sense? Tomorrow, so we are out of time. Tomorrow I will finish off with the other two past papers that I have, and I'll get some additional questions because I see we're actually moving through this work quite quickly. And then hopefully by the end of tomorrow, you guys are all bosses on electrodynamics. Everyone good with that? Yeah. Cool. Enjoy the rest of your day, guys. See you tomorrow. Same time, same place.